start recording. And yes, so I will hand it over to the speakers.
Thank you. Sorry. Thank you, Victoria. Welcome, everyone. Thank you for being here for this first talk of this stochastic optimization study group. So as Victoria mentioned, today we're going to give an introduction on stochastic optimization. So the talk will be in two parts. In the first one, I'm going to present general concepts of stochastic optimization, and in the second part, Alejandro will present an example to illustrate them. So to begin with, I wanted to present a broad overview on optimization. Okay, so that we're on the same page. So optimization is about making a choice among a range of possible options according to some quantitative criterion. Okay, so we want to have quantitative comparison between our choices. Mathematically, to represent this, you consider that you have a set that contains all your possibilities that we call a feasible or admissible set. And this criterion is also called a criterion or a cost or objective function. That is actually a function that takes its value from the admissible set and that is valued in the set of real numbers. Okay. And typically we usually consider minimization problems, okay, and we write the fact that we want to minimize this function over the set X in this form, okay. And we say that we have a solution of the problem if that here is called X star, if we have an admissible point. So yeah, in the following, I will call elements of this set admissible points, feasible points, or decision variables, just when I want to change. So yeah, the solution is an admissible point.
You have a photocopy of a crane.
Crane.
Yes, a bird. Some kind of bird.
The value
A crane.
at this point
It's a kind of bird.
lower than the value of
We can find.
Sorry, I think someone is not muted.
Yes, I think you can mute everyone. Mute. Mute, probably. Yeah.
Okay, I think now it's okay.
Yes. Okay, so that's the definition of a solution. We'll not go into more theory, just to be clear. Okay, so this problem is very general. What can we say about admissible set and cost function in general, when usually the nature of an admissible set will depend on the nature of the decision, and we have very classical discussions concerning the fact that maybe our decision might be discrete or continuous, finite or infinite dimensional, static, dynamics, and many others. Okay. There is one representation that I want to focus on during this talk, which is the one created by a finite set of inequality constraints. So typically you suppose that your set is a subset of some space, typically vector space, such that finite number of inequality constraints are satisfied. Okay, so here the inequality must be understood component by component. Okay, and so we're going to focus on this view for the admissible set. So I'm going to give some examples of constraints that you might encounter in applications. Typically, you might have physical restrictions. If you consider, I don't know, temperature variables, you might want them to be positive or at least non-negative. If you consider networks or the kinds of system, you might have equilibrium laws or any physical laws that might be relevant. You might also have hard goals to achieve. If you work in system theory or in control theory, you might want your system to achieve to reach some targets. If you work in the plant management, you might have production objective to meet, and you might also have safety issues. Okay, you want figuratively to stay on the road, okay, to stay in some set for safety. You might, if you look at this problem in another way, in opposite way, you might want to avoid some sets, and so on and so forth. So yeah, many ways, many problems actually can be represented with this formulation. Okay, so that's it for the admissible set. Concerning cost function, usually, as I mentioned, this is the function that allows you to compare the available choices, and you can also characterize a problem depending on some properties of the function and the constraints. So typically, if your functions here are linear, you have a linear problem, and you can combine with the previous one. You might have linear finite dimensional, linear infinite dimensional, and so on and so forth. You have also the same discussion with differentiability, convexity. Okay, so I'm not going to focus on this. Just want to mention it here. And well, as examples of objective functions, you might have actual cost to minimize, like fuel consumption, expenses, and so on. You might, if you look at the problem in the other way around, you might have a profit to maximize. Okay, if you work in finance, it might be a return of investment, maybe number of sales, and more generally, you might use any performance indices like time, distance, velocity, and any combination of this and anything that actually fits the framework. Okay, so the main point of this introduction is to understand that we will deal with problem of this type where we want to minimize some function subject to some constraint. Okay. One of the main points of today's talk is to understand what happens when you might encounter unpredictable events during your optimization process. So why do we care about this? Well, it is because in some applications, and actually many of them, you might have such uncertain, unpredictable events. So if you work in power systems or inventory management or any kind of system that needs to deal with demand, okay, an exterior demand, well, usually you don't know it beforehand, so you have uncertainty on it. If you work in finance, usually you have risk in the share markets. So typically you don't exactly know what is the time evolution of the share prices, okay? If you work on biological systems, you might have the influence of the climate, of the predators, or any other environmental factors that are not clearly known. If you work in system stabilization, usually your system is not represented perfectly, so you have modeling errors. You have also usually noise on the measurements, which means uncertainty, and so on and so forth. Okay, so in many applications, you have to deal with some kind of uncertainty. Okay. So how do you represent it? Well, usually we consider the uncertainty to be some unknown parameter belonging to an uncertainty set. Okay, so here the parameters will be called D, and the uncertainty set will be this calligraphic D. In the optimization context, we suppose that this uncertainty acts on the cost. So we have a new cost depending on the decision variables and the uncertain parameter, and it also acts on the constraint in the same way. So we have a new constraint. There are two main issues that maybe I will address from now. The first one is kind of intuitive. You know, when you have something that is unknown, maybe you want to get information of it. You know, maybe you want it to be less uncertain. Okay, and if you cannot, well, maybe you want to write a proper uncertain optimization problem. You want to deal with it. So yeah, so for the first question, I kind of spoiled it. You want maybe get information. You want maybe know what happens when you can observe this parameter D. And for the second one, well, you might need to, well, usually you have to model the uncertainty in some way. Okay, so concerning this, the first question, there is a very classical discussion when you are able to observe at some point the uncertainty. It is the discussion of observation first or decision first. So when you are able to observe the unknown parameter, there are probably two cases. One when observation comes before the decision. So you have observation first. In this case, the unknown parameter D ends up being known actually. So in this case, it makes sense to minimize this cost. Okay, so I didn't mention it, but when D is unknown, it does not really make sense to minimize directly this cost with respect to X, because for fixed X, you don't really know the cost associated with this or the constraint. So you cannot really make a decision if you don't know how to compare. Okay, but in this case, since you have observed the unknown parameter, it is actually known, and you have a parameterized problem and parameterized solution. So here you don't have any uncertainty anymore, but it will be relevant later on. So for the moment, we are concerned with the case where when the observation comes after the decision, so we have decision first. In this case, D remains unknown, and actually the problem that we'll be treating will depend on our representation, our precise modeling of the uncertainty. And there is one pitfall we want to avoid, and which is we might be tempting. It's to consider one value of the value that I will also call this particular value maybe scenarios. Okay, so there is to the pitfall to avoid is to focus on one value and work with this one only without considering the other ones. So it might work, but if you do this, you kind of remove all the ignore all the uncertainty in the problem, and it might not be very efficient sometimes. Okay. So now I'm going to start presenting the different types of uncertain problem you can write, and I'm going to start with one which is not stochastic, but I think it is still important. It is the worst case approach. So in this situation, consider that you consider every possible choice or possible values of every scenario identically. Okay, you do not put precise probability for the moment. Okay, you do not consider them different in terms of occurrence. Okay, and you make a decision based on the worst possible value of the cost that you might find. Okay, so precisely in terms of the cost, it means that for a fixed value of x, you will consider that the value of d that you get will maximize the cost. Okay, with respect to d. And everything happens as if you were in some way playing against nature. This is often how we represent it. And you assume that nature response, so you play first, okay, and nature response is the worst for you. So nature has some kind of opposite cost, is the opposite cost of yours. Okay, so nature has the worst. So this is how you describe the worst case cost. For the admissible set, you have something that is very similar. Okay, so you want to choose the x's such that all the constraints are satisfied, so the maximum constraint is satisfied. Okay. This formulation is called a robust formulation. Okay, most of the time, and we can make several remarks about this. The first is that if you look at the problem and how the uncertainty really acts on the problem, well, it does not really depend on particular values of d, okay, but more on the set itself. So it is the typical meaning of the sentence that every values of every element of the set d is considered the same. Okay, and okay. Another point is that this kind of formulations are very safe, okay, because typically we want the constraint to be satisfied for all d, so we're taking all the uncertainty into account, okay. But as a result, they are very restricted, okay, and usually not efficient. So if you can take an example, a very simple example, suppose that you want to drive home and you're on a road that you want to drive home as fast as possible, and you're on a road that might be sleepy sometimes, but you don't know, so it might be dangerous, okay, sometimes, and you don't know exactly when. And if we are in this setting of decision first, you will not have this information before you take the decision. So you have to deal with the uncertainty as it is. And if you use this worst case approach, you will consider that the road is always sleepy, always dangerous. So you will typically react accordingly and drive slower and everything that is careful. Okay, so the problem with this, the advantage is that you know that whatever happens, you will not get out of the road. Okay, get off of the road. Sorry, but you will get home very late because you will not be very fast. And this type of properties is called conservativeness. Okay, we have a conservative approach, and usually we want to avoid it. And one very typical way of doing this is to have a stochastic approach. Okay. So now I'm going to present different type of stochastic optimization program. Okay, first, the general idea of stochastic optimization is to consider that the situation that occurs, the value of the uncertainty, are actually different because they have a different probability of occurrence. Okay, so we will use this in the representation of our problems, and And formally, that it means that we will represent our certain parameter as a random variable that value typically in the uncertainty set. Okay, so now we have some kind of probability distribution instead of just a set. So maybe the simplest stochastic optimization problem is the case where you have an expected cost. Okay, so the idea is to make a decision not on the worst case, but on the average cost based on an aggregation of the scenario, of a clever aggregation based on the probability distribution. So the cost is basically just the expectation taken for every x taken with respect to d, to the distribution of d. And here we do not focus on the admissible set, it might be anything. So we've got several remarks about this type of formulation. And then, so I do not write the optimization problem, but it's, it's basically written in the same way that the general one. Okay, we have here the admissible set and here the cost, but written in a specific way. So I've got several remarks. The first one is that unlike the worst case scenario here, we have the uncertainty characterized by the probability density, and this will be the case for the other methods, the other representations. This is typically less conservative, okay, so a bit more efficient than the worst case scenario, but less safe because you do not have any restriction or you do not take into the uncertainty into account in a very hard way. You barely just want to minimize the average cost. So what it means when you take the average in this is that you don't really care what happens about specific realization, okay? You just want to have some minimization information. You want to minimize some average case. So it would make sense if you repeat this optimization process many times, and you want to look at what is the empirical mean of the cost, and you know that it will be minimized. So you have very few restrictions, but yeah, you usually gain efficiency. And another cool property of this is that if this function has a nice property with respect to x, when with the expectation you keep them. So as I mentioned, it might be interesting so that it fits some frameworks that I presented before. Okay, so that was for the case of expected costs. You can do the same basically for the constraints. So here the idea would be to put a constraint in expectation. So you put a restriction on the average value of the constraint. So we don't really care about the cost in here. I mean, we care, but we don't specify it. And the admissible set here will be the constraint will be the average constraint with respect to the uncertainty, to random variability. So I've got several remarks here. I would say that generally it's a bit safer than the expected cost case because you actually add some uncertainty, information in the constraint. But again, it's not very intuitive because if you go back to the car example, having a constraint in expectation again does not imply anything or very indirectly something about the precise realization of what happens. So if you take a decision based on the expectation here, it will probably take into account the fact that the road might be dangerous, but the direct implication is not clear. However, this formulation is very interesting because here the constraints also keep the properties of the original constraint. So it might be, all this might be resulting in problems that are quite easy to solve, okay, with nice properties. Okay, so that's for constraint and expectations. The last problem I want to present in this decision first setting is the case of change constraint problem. So here the paradigm is a bit different. We care about the realizations of the specific realizations of the uncertain parameter, and we want to put a constraint on the probability of admissibility. Okay, so here we do not specify the cost, but the admissible set will be a bit different. Here we put a constraint, we choose the x such that we have a constraint on the probability of admissibility. Okay, so yeah, so I was there explaining about chance constraint problem. So the idea is that we want to put a constraint on the probability of admissibility. Okay. And here there is a parameter alpha such that is a risk that one would choose, and basically want to have this 1 minus alpha closer to 1, but maybe not equal to 1, because if you want to have this satisfies almostly, so with probability 1, it might be too restrictive. Okay. So usually we want this to be close to 0, but not equal to 0. And actually, what you can say about this formulation, it is a stochastic equivalent of the robust formulation. And it is typically less conservative, but we still this idea of having the constraint satisfied for not all, but a lot of the possible values of D, and maybe the most relevant ones, in the sense that the most likely ones. Yeah, because now if you consider again this example with driving on a road, on a potentially dangerous road, you will not act as if the road was always sleepy, but maybe just you will take into account that, okay, if it is potentially in some dangerous turns and things like this, you might take into account that the fact that, okay, if it is dangerous at this point, I have to maybe to be careful, but yeah, usually you will be much faster. So this constraint is softer in the sense that you change safety for efficiency. Okay. The main inconvenience in this formulation is that the set that you get here is usually complex. Okay, so you still have some kind of inequality constraint, but if you consider the function of x, if you consider this probability as a function of x, usually even if this is here, even if you have convex set here, convex function here, in the end you don't have anything convex and you don't have anything simple. So you have to be careful in the way you deal with it. Okay. So that was it for this, for the problems with this idea of decision first. Okay, so there are several other ones, but I don't want to mention them because from the introduction it might not be relevant. And now I want to go back to this idea of decision first and observation first, and wonder what happens if we can do both. If we can make two decisions, one before observing and one after. So usually the process is the following: you might choose some first decision variable in this set x0 and have an associated cost. Then you might observe this. Now that you know D, you will choose your second variable as a function of D. Okay. So it will be a random variable, and you pay the associated cost. And now once you write the program, you obtain what we call a two-stage problem, in which the optimization variable, decision variables, are elements of x0, and the second decision, is a function that we call a recurse function here. And it's important that it is a function because you want to represent the fact that you have information during the second decision. And since you make a decision, if you make a decision here, you don't really know what is the value of D when you make your decision. If you think about it, if you want to represent this problem and here you have this uncertainty represented by a random variable, you want to represent the fact that just simple values of x1 might not be a good way of representing it, because you do not represent the fact that you will know D during the second step. Okay, so very important here for this type of problem. Usually in the first step you have values of the set, and in the second step you have function of this random variable. Okay. So what's important here is that even if these sets are finite dimensional, the problem will be infinite dimensional because you work on a set of random variables. Okay. And usually you just quickly solve this problem in the backward way, meaning that you solve first the second step and then the first step. So this is okay, a bit tricky, and this formulation can be extended to multi-stage problem when you have not only two but several, maybe arbitrary numbers, fixed but arbitrary numbers of decision. Okay. So that was it for problem with recourse, and this is basically it for the different types of problem I wanted to present. Now I want to talk a little bit about numerical methods. Okay, just broad view on numerical methods that are available for this type of problems. I've got two general remarks. The first one is that we can combine the formulation, so you can have expected cost with change constraint. You might have expected constraint with recourse, and okay, so you can combine the concepts. And secondly, when you look at the problems I just presented, there are particular versions of the general one I call PC with the cost and the constraints, okay, where the costs have particular structures, and typically they are hard to compute because when you have any type of probability distribution, computing the expectation of some function might be just impossible to do analytically. So you don't really know how to compute analytically the cost, but since you have some some structure with the probability expectation, you might come up with methods that take take advantage of this. Okay. So as example of numerical methods, for the different cases I presented, you have for the expected cost, typically stochastic average approximation. This is a version of Monte Carlo sampling. Okay, this can be applied to other cases, but I'm mentioning it here. Maybe the most famous one for this type of problem is what we call stochastic gradient, which is a variant of gradient methods. And you might also have second order methods and so on and so forth. Okay. In the case of, here it's basically in the case when you have an unconstrained problem or problems with a simple constraint, basically. For the case of constraint in expectation for people who are accustomed to numerical optimization, you have dual methods and primary dual methods that are specifically designed for this kind of expected constraint. In the case of change constraints, so since this, you have a very specific and very difficult set in general, there are several reformulations that you can make. Typically, in the case where you know the probability distribution and you can actually compute this constraint, okay, when you have this deterministic reformulation, typically when you have linear constraint and Gaussian distribution, everything is nice. You might also end up with approximation, typically inner approximation. So you restrict the set that you consider, but you have a nicer way of writing it. And when you cannot do this, typically you do what is called the scenario approach. So you sample several values of the uncertain parameter, okay, according to the distribution, the probability distribution. And then you enforce the constraint only on these scenarios, and you hope that if the number of scenarios goes to infinity, then you will end up enforcing this constraint in probability. Basically, and for multi-stage problems, there are many ways. You do dynamic programming, scenario trees, reinforcement learning, and so on and so forth. Okay, so that was it for the general presentation, general introduction on stochastic optimization. Now Alejandro will present an example and illustrate the different concepts for this using the example. Okay.
Thanks, Emilian. Can you see my screen to check that everything's fine?
Yeah.
Cool, thanks. Right, so I just want to emphasize that this talk is trying to lay some foundations about introduction to stochastic optimization, and Emilian has presented some basics that I want to now put to the ground into some specific practical problem. So I'm gonna present some slides about the Nusswende problem, or a variation of it, in which you have a company who decides to order a quantity of a product X, and then you have a certain demand D, which is unknown when you're purchasing. So now we assume the cost per unit is denoted by C, and then you may have two cases. So one of the cases is you could have that the demand is greater than what you actually ordered, and in that case, you need to make the decision and buy more units at a more expensive price, which is denoted by B. And of course, B is greater than Z, and this is called the back order penalty. Now, on the other case, it could be the case that the demand that you observe then after you purchase is actually smaller than X, so smaller than what you ordered. And in that case, you incur in a holding cost of keeping these extra items in store. Now, this is denoted by H, and therefore the total cost for this problem is written in this form. So it's a cost function that depends on the variable X, like the units you're buying, on the unknown demand as well. So this is the total price that you for the items you order, and then these are the two cases. You either get a demand that's greater than X, and therefore you incur in this cost, or you have a demand that is smaller than X, and then you incur on a holding cost. So the objective of here is to minimize this total cost. X is the decision variable and D is a parameter. Now, this cost function, you can write it in a different way. So this just simple algebra, you have a maximum of these two objects. And by inspection, you can see this is a piecewise linear convex function. And the minimum is actually attained at X equal to D. This is, of course, this only holds if the demand is known. So in the simple case where you know the demand, of course, this is the obvious solution. You will always order the demand. Otherwise, you will incur either in holding costs or reordering costs. Now, what happens when D is unknown, which is the context of this talk? So you have to make the ordering decision has to be made before the realization of the demand becomes known. So in this context, we're viewing the demand as a random variable, and we denote it as a capital D to differentiate it from the small d, which represents the particular realization of D. So I think Emilian pointed this out a bit. So a silly attempt would be to try to optimize this problem straight away. But this problem actually doesn't make sense because fx of D is random. So here I have two realizations of the demand, and it's highly likely these two functions are different. And of course, there's no one x that can simultaneously optimize both functions. So trying to just optimize a random cost function doesn't really make sense. So there's attempts that you could do. So one would be plan for the average case in the sense that let's suppose that the CDF of D is given by some h of x, which is the probability of D being less or equal than x. And we denote mu as the mean value of this random demand D. So now one attempt to do is just think about, I'm going to plan to buy always the average of the demand. So in this case, the cost function is basically fx of mu. And because we already know that whenever the demand is given, the obvious solution to this is mu. So I'm always going to buy. So the optimal policy is always buying quantity mu. But then the problem about this attempt is that if your demand is actually fluctuating a lot, then this could incur actually in a lot of costs in the long run. And we'll illustrate this by an example later on. So another attempt is something that Emilian already touched on, is plan for the worst case. So I'm just gonna try to apply it to this problem. So let's suppose that somehow we know that the demand, we don't know the actual demand, but we know that it sits between some lower and upper bound, L and U. This could be either by some economic knowledge or some statistical knowledge as well. Now, in this context, we know we need to minimize the maximum of f on that interval. And this means that we'll try to make a decision that when I'm prepared for the worst possible outcome of the maximal cost. So I'm trying to be safe, basically. You can show that, and I'll show the proof if there's time. I don't think there's time, so I'm going to avoid the proof. But you can show that the optimal solution is this one. So it depends on the holding cost h, the upper and lower bound L and U, and also the reordering cost B. So one thing to note here is that if the holding cost is 0, then the optimal solution is U, which is the upper bound on D. And this is, it makes sense because you don't incur any cost in holding, so you can always buy the maximum, right? Then, of course, this is often conservative, as will be illustrated later on as well. I'm going to skip the proof, which is quite simple, and then move on to a suitable framework, which I think Emilienne tried to motivate, which is the stochastic framework. So now we assume we know the probability distribution of D, or one thing to point out as well is that you could also sample from this distribution, but we're not actually touching on that issue on this talk. But let's assume we know the probability distribution, and now it makes sense to talk about the expected cost as a function of x. So we're trying to minimize the expectation of the cost. So it's like a long run problem. And then as a consequence, the problem we want to minimize formally is as follows. So we want to find all the items, the minimum of f of x, which is the expected cost. And recall that d is a random variable. So this means we're optimizing total cost on average. So it turns out that this news vendor problem is actually really well studied, and it's most likely always the first problem that textbooks present because it has a closed form solution. And I recall that the CDF of the x is written like it's denoted by h of x, and the solution to this is equal to the quantile x star equals to the inverse of the CDF, and it depends on the reordering cost b, cost per unit, and holding cost h. So of course, it's not always easy to get a closed form solution, and that's why in general you solve stochastic programs using numerical optimization, numerical methods. And that's why with this talk we want to open the door, because within this study group there's going to be a lot of talks regarding numerical methods and other specific problems. So we want to just point in that direction as well. So I could quickly show the proof. This is basically using properties of the cost function. You use fundamental theorem of calculus to write the cost function like this, and then you just compute the derivative which sits inside this integral by using the expectation. And because if you remember, there was two cases, either the demand is greater than z or smaller than z, then you can use this fact to write this expectation as these probabilities, and then these probabilities can be written in terms of the CDF. So that's like the sketch of the proof is not difficult. And at the end, you can write the cost function as follows, and compute the minimum. You just take derivative of the right-hand side, equate it to 0, and end up with this equation. And from this equation, you get the result I just showed you in terms of the inverse of the CDF. So for this particular example, I repeat, you could obtain a closed form solution, but it's not common at all. Now, I'm presenting a numerical comparison to illustrate some of these comments I've made. So recall that the cost function is given by this. I forgot to say these brackets just represent the maximum between what's inside and 0. So this is equivalent to the maximum of d minus x and 0. Just for simplicity. And then we assume that cost per unit in this example is 1, and reordering costs is 5, meaning if I don't buy enough, like if my demand is greater than what I order, then I'm going to incur in a large cost if I need to reorder items. But I can buy a lot of items, and maybe my demand is going to be lower than that. And in that case, I can hold these items because it's not going to be that expensive. This will make sense with the numbers I present. For simplicity, we assume the demand is normally distributed with mean 100 and sigma, or standard deviation 14. Now, I present here the optimal solution for each of the 3 cases I've presented. So we plan for the average demand. This is always going to be 100 no matter what these values are. So I'm always going to buy the average demand. But we'll see that this problem actually, the demand fluctuates a lot. So it's not going to be the best solution. And then we have here the worst case approach, in which we have some knowledge on the lower and upper bound of D, but we don't know what D actually is. And for this case, the optimal solution gives you 134 units of product, whatever that product is. It could be a newspaper or anything. And then if you plan for the expected cost, which is the stochastic approach, it'll give you 112 units. So you can see here, you're getting, for these two cases, higher units than the average case. And it's because of the reordering is more expensive than actually holding the items. Now, in the next column, because if you recall, all of these three are minimizing different costs. And in order to compare apples to apples, I wanted to see, okay, these attempts tell me how much to buy. And now I'm going to assess if using this, how much it's going to cost me in the long run. So I compute the expected value of the cost by using each one of these three. And we can see that the worst case, of course, gives you a more conservative, more expensive cost, which is a more conservative approach because it's safer. And the expected cost, or for the stochastic case, is smaller than the average demand. And it is due to the fact that the demand is actually fluctuating quite a bit. So now a quick slide before wrapping up to touch on chance constraints, which Emilian also spoke about. We know that if the problem has could have large perturbations or could fluctuate a lot, it means that particular realizations of the demand, this cost could be quite different from the expected cost. So a natural question would be, can we actually control the risk of the cost to be not too high? So how do we do this? We could either try to impose an upper bound tau on the cost for all possible realizations of D. So D sits on this set. But then if this set is large, then this condition becomes really restrictive. So then another approach is to introduce a constraint improbability. So you want that improbability, hopefully with high probability, that the cost is upper bounded by tau. And for this particular problem, you can write this probability constraint or chance constraint with respect to the CDF, so it's more amenable for analysis. So it's just a quick talk about how you can actually, or how these constraints come from different problems, and you can write them differently. And now to finish the talk, I want to mention that this new span of problems is a simple example of a two-stage problem. So the first stage is you make a decision before actually knowing what the demand is. And that decision is how many newspapers you buy, for instance. Then at the second stage, you observe the demand, and this is the random stuff that nature will give you. And for sake of an example, let's suppose that that random stuff that happened is actually the demand is greater than what you bought. So in the second stage, you need to make a decision and take a recurse action of ordering the extra newspapers at a higher cost in an attempt to repair the havoc. So here I must emphasize that we're not, the recurse function is actually given. So we already know that if the demand is greater than X, then we do A, and if the demand is smaller than X, we do B. We're not actually trying to find it. So the evolution of information is of paramount importance in these types of problems. And with that, I want to finish off this talk. Thank you for your attention, and sorry for the problems, technical problems.